everyone is there. This, James K. And this one. Okay. Okay, good afternoon, everybody. Welcome you to SCI33205. I hope that everything is fine. All right. Okay, we go to our lecture notes, right? Just and today many of you, especially the students from M605 has spent time, needs to spend time in a hospital at Lama Tibadi Hospital. I don't know for what purpose, but it's good thing that you just okay. As usual, you just type your name, okay, in the chat box so that we could recognize each other that you appear here in the like that, okay, so that we can recognize that you appear in the classroom, right? What I forget to mention, okay. Okay, let's go ahead with our story. This is some detail, right, of the creating. Okay, you have already seen some application of the have you seen this already, right? The I don't know, last time we arrived at ถึงตรงไหนครับมีคนไหนจำได้ไหมเอ่ยนะครับกลับไปกับเดี๋ยวผมขอเปิด60413 right no not this one อันนี้ขออนุญาตไม่ใช้ไฟล์นี้เพราะว่าผมดันไปแอดงานวิจัย 5 Ultraviolet okay we arrived here and yeah that's the unit wavelength, right? It's the wavelength for the ultraviolet. I'm not sure whether okay พระนะใช่นะครับ okay พระนะใช่ and where is the mouse? Okay, here พระนะใช่ okay we arrive at the ultraviolet, right, which is the frequency band below the, I think, over, okay, above the typical visible light for us that the human eyes can detect, right? What is the reason why I say it's the band above the typical light? Because the frequency band is higher here, okay, because you have shorter wavelength. Shorter wavelength means you have higher frequency, okay. That's why we say it's the frequency band above the visible light, and the wavelength, okay, is given from 0.6 nanometer until 400 nanometer. And what is the source of this visible light? Oh, no. No. ชัยกฤษนะครับชัยกฤษโปรดดูที่รายกลุ่มนะชัยกฤษสอบของมสวนะครับของ EE 111นะครับเข้าอีกกลุ่มหนึ่งนะครับคุณดูที่รายกลุ่มนะชัยกฤษออกไปนะครับอันนี้มันเป็นของมปลายนะครับokay this is the sun, right? The sun, which is the source of the ultraviolet light, and yes, and the ultraviolet is the cause of suntans, okay, that will burn our skin. All right, and most of the UV lights come from the sun, and our skin and the atoms in many living creatures, not only human, we absorb the ultraviolet. Okay, and some of the ultraviolet will be also absorbed in the upper atmosphere, and the name of that upper atmosphere is called stratosphere. In the stratosphere, the ozone is generated by ultraviolet light, and it's the reaction between oxygen and ultraviolet radiation. Ultraviolet is used for human on Earth in the sterilization, okay, in order to keep some milk to stay longer, to last longer, and it's used also for vitamin D production to human body. And unfortunately, the ultraviolet light is a cause of cancer. And now we arrive at almost the last type of the frequency band by electromagnetic waves. For those of you who want to attain or who want to be on leave because you need to attain the the special duty, okay, so that you can apply for the doctor education program at some university, just leave me the letter of leave or photo of leave. Okay, when you are there, just take a photo and send me by email or by line. Okay, but it may not happen with you in M604. Most of them are in M605. Okay, now let's talk about X-ray. X-ray is maybe quite familiar to us because you may have ever heard the word X-ray when you go to the hospital to see something in your chest, right? Okay, yes, X-ray has the wavelength from 10 to negative 19 meter, or in terms of appropriate scale, it's called 0.1 picometer. You know, pico is 10 to negative 12, right? And you have one additional negative 1. You have an additional negative 1 here. To the longer, the maximum length, which is 10 to negative 8, it's called 10 nanometer. The most common source of the X-ray is, it can be is generated by human also. It can be the acceleration of high energy electrons. Okay, that is the electron is generated, is accelerated, and it hits a metal target. And in terms of nuclear physics, it's called a bombardment or bombarding, like this. Okay, X-ray easily penetrate or damage, destroy living tissues or organisms. we we use this for special purpose. Your body is not allowed to receive X-ray for a long time. Okay, only a certain time, and after that you need some time to recover your body. And if you want to make X-ray later, you need to take rest. Okay. It is used as a diagnostic tool in medicine, and yeah, the good thing. Okay, it is also one of the treatment for certain form of cancer. And now let's talk about the most dangerous type of the electromagnetic wave. It has the highest amount of energy. I'm not sure whether you can hear me well or not. เสียงได้ยินนะครับที่ซูมนะครับ yeah, it's called gamma rays. Okay, you may see or know later that gamma ray is caused by the nucleus of several isotopes, several unstable isotopes. Once they cool them down, okay, to have the stable state, they are gonna release those nuclei will release the gamma rays, okay, which is a kind of photon, but it's the photon with a very high amount of energy. Okay, what about the wavelength? The wavelength of gamma ray is from 10 to -14 to 10 or in spatial scale, you know, this is femtometer. Maybe I have already explained it to you. It's 10 to -15, sorry, 10 to -15, and once we have 10 of that, it's going to be 10 to -14. Okay, this one is called femtometer or Fermi. And after that we have 10 to that the maximum length, right? Maximum length of the wavelength, it's 10 to -10, or it's 0.1 nanometer. Okay, which is very small, less than the visible light. Okay, yeah, as I mentioned, it's the gamma rays are emitted by radioactive nuclei. Okay, nuclei is the plural word of nucleus นะครับก็คือรังสีแกมมานะครับถูกสร้างขึ้นมาจากการลดเขาเรียกว่าอะไรลดการสั่นไหวลดคือนิวเคลียสนะครับพอเขามีปริมาณมากๆแล้วนะครับพอมีขนาดใหญ่นะครับเขาจะลดขนาดนะครับเนื่องจากว่ามันไม่เสถียรนะครับมีอัตราส่วนโปรตอนหรือว่านิวตรอนที่ใหญ่ไปอย่างเงี้ยนะครับมีอัตราส่วนโปรตอนนิวตรอนที่ไม่เหมาะสมอย่างเงี้ยนะครับธรรมชาติก็จะทำให้นิวเคลียสนั้นครับลดขนาดลงก็คือแตกออกมานะครับพอแตกออกมาแล้วนะครับก็จะมีปล่อยรังสีเนาะรังสีก็ได้แก่พวกอัลฟาเบต้านะครับอัลฟาก็เป็นนิวเคลียสของฮีเลียม42นะครับแล้วก็เบต้าก็จะเป็นพวกอิเล็กตรอนหรือว่าโพซิตรอนนะครับแต่ว่าเมื่อลดขนาดตัวเองลงมาแล้วนะครับก็ยังไม่เพียงพอนะครับในบางครั้งนะครับเขาก็จะเรียกว่านิวเคลียสที่แตกออกมาแล้วนั้นนะครับก็ยังมีการสั่นไหวอยู่นะครับก็จะลดพลังงานตัวเองครับเพื่อให้หยุดการสั่นไหวเนาะเพราะว่าตัวเหมือนกับเรายังร้อนอยู่นะครับยังร้อนรุ่มอยู่ก็จะสั่นไหวนะครับเพื่อให้ลดการสั่นไหวนะครับเขาก็จะปล่อยพลังงานออกมานะครับเพื่อให้ตัวเองอยู่นิ่งพลังงานแบบนั้นนะครับเราเรียกว่าเป็นรังสีแสงคือโฟตอนนี่แหละนะครับแต่ว่ามีพลังงานสูงมากนะครับสูงมากเราก็จะเรียกว่าเป็นแกมมาเรย์นะครับดังที่เราเรียนในเรื่องนี้นะครับ okay and that's the reason why we have the gamma ray. Yeah, as I told you, it's a very dangerous ray. Actually, it can penetrate very well and cause serious damage to human tissue when our living creature tissue absorb them. Okay, it's dangerous. Yeah. What about the next aspect? In gamma rays, if you work somewhere there, okay, if you work somewhere close to the source of the gamma ray, you have to wear a spatial protection cloth, okay, but I don't think it's possible, because to be safe you need to wear the cloth which should be made of lead, you know, PB lead, and in the scale of several inches. It's impossible actually. Okay, the normal clothes would not be appropriate for us to would not be sufficient for us to protect the gamma rays. All right. Okay. Now let's talk about the next thing. You have to wear the clothes by garment that can heavily absorb the gamma rays. For example, several layers of lead. I think it's very difficult to have such clothes. And ถ้าไม่มีใครเข้าอีกแล้วขออนุญาตปิดซูมนะครับ Okay. Okay. Let me upload the problem to exam for the bachelor degree. Okay. What about the good thing? What is the benefit of the gamma rays? It is used for nuclear medicine. Okay, and it's used also for security purpose. It's used also for medical diagnosis and to cure some types of cancer. We use also the gamma rays, and there is also there are also other application from gamma rays. But if you absorb the gamma rays accidentally, you may get cancer easily. Okay, that's the bad thing. As the wavelength reduces, as you can see before, when the wavelength reduces, the energy of the emitted wave increases, right? When the frequency band is higher, you get a higher amount of energy. And if you go to chapter 6, okay, there is a formula which is called Planck constant. It's equal to E equal to HF. Okay, so when the frequency is greater, you get more energy. Okay, but we will not talk about that in this chapter. All right. Now let's talk about the big scale of the electromagnetic frequency band. All right. Here you have several kinds of application, right? As we have seen in the text, and you can see the wavelength from the highest amount, okay, the greatest amount of wavelength, to the shorter and shorter and shortest at the gamma rays region. All right. โอเคนะครับระหว่างที่ผมสอนนะครับรุ่นพี่ขอสอบเวลานี้ด้วยนะผมก็เลยต้องมอนิเตอร์เขาอีกเครื่องนึงครับแต่ไม่เกี่ยวกับคุณครับคุณเราก็เรียนของเราไปนะครับโอเคthis is called extremely low frequency band. Okay, there could be many names of bands in electromagnetic wave. This is called extremely low frequency. It has spatial feature. It's safe. It's beneficial. If you receive it in appropriate dosage, okay, it's still safe for us because you know the reason why, because it has low energy. But if you go further, when the wavelength is decreased, okay, when the wavelength decreases, we have a little bit higher amount of energy. It's called very low frequency region. Okay, here you can see this amount, this electromagnetic wave. It can be emitted from the electrical socket, okay, at your home, and there will be also some electromagnetic wave induced from the transmission lines on the transmission tower. For example, in Thailand, we have this such kind of towers next to the road, right? On the road, we once along the road we have the tower, and yeah, you can get the very low frequency electromagnetic wave from this tower. And let's move to a little bit to the right. You can see that the length of the wave is shorter and is known as low frequency band, okay, low frequency region. Human uses this band for the purpose of television and radio and several kind of broadcast television. What about the dangerous? What about the dangerous stage? It's almost safe, okay, low danger. If you stay close to the television tower, you would receive something which is not very harmful to you, okay. And once we go further to the right, the wavelength is shorter, okay, compared to the original, the beginning one. Human uses this band for radio transmission, for wireless communication, and it starts to be a little bit dangerous, okay, if you stay in that place in a very long period. Yeah, once we move further, we're gonna reach the microwave region, and human use this band for the purpose of wireless communication, like your smartphone, your handy, your mobile phone. And in order to, this is used for communication, right? For talking, for sending the message, for transferring some information that you want to send, right? But in another sense, if you really want to get the heat or the energy, human design that device, which is known as microwave oven, okay. But still, these devices use the same band, frequency band, as the one in wireless communication, but for spatial purpose, they're gonna transmit very high amount of energy in this microwave oven. And if you go further, it's called it's gonna be the band for satellite communication, which is a kind of long transmission system. If we go further, it's gonna be called infrared, right? We use this for television remote control or something like that, and it's gonna bring you some heat, okay, with this one. And once we go further, as you know, the wavelength is gonna be shorter and shorter, and we reach the visible range of the light. Okay, it's generated mainly from the sun, by the sun. And if you go further, okay, let's talk about the danger from this one. It's still safe and beneficial in appropriate dosage. Okay, if you spend time in the morning, you can improve your body because you can get vitamin D, okay, from the light by the sun. And let's talk about the ultraviolet region. Here, humans need to wear the sunglasses, okay, in order to protect the tissue in your eyes, okay, because the energy is high, okay, if we watch the sunlight for a long time. And let's move further. The wavelength is shorter and shorter. It's called X-ray region, right? We use X-ray to see through what's going on in human body. For example, here is the hand of the human. And once we go further, we reach the final band of electromagnetic wave. It's known as gamma rays. Okay, the wavelength is very, very short. You can see the frequency band from 50 hertz, 1 megahertz, 500 megahertz, okay, for radio, and 1 gigahertz for data communication, 10 gigahertz for satellite for microwave, 30 gigahertz for infrared, 600 terahertz, that's the frequency for the visible light, and 3 pentahertz for the ultraviolet, 300 pentahertz for X-ray, and 38 hertz is the frequency band for the gamma rays, which is very dangerous, right? Here, in both region, X-ray and gamma rays, it's extremely harmful to our human body. But once, if you take a look at this band in terms of wavelength, it's gonna be 6,000 kilometers, okay, which is very, very far. 300 meter, 60 centimeter, and 1 foot, okay, till 3 centimeter, 10 millimeter, and the order of nanometer for the visible light, in 100 nanometer for the ultraviolet UV light, and very, very short 1 nanometer, 10 picometer for the extreme band like X-ray and gamma rays. Okay, you may not often hear these two bands because they are very dangerous. You can see them only in special occasion like at the hospital and so on. All right, that's the whole picture of the electromagnetic wave band, okay, in terms of frequency band. Now let's talk about the little bit an example for the computation of the wavelength and the frequency for the electromagnetic wave. Okay, it uses the same expression as I told, you may have seen during our on-site class. We have C equal to lambda f, right? And the lambda is the wavelength, f is the frequency in terms of hertz, c is the speed of light. And in our level, we can oh my god, oh, โอ้เดี๋ยวแป๊บนึงนะครับผมซูมนั้นนะครับไม่ได้จ่ายเงินจะมีปัญหานะครับขออนุญาตแจ้งปริญญาตรีนิดนึงครับ All right, let's talk about the computation in terms of C and lambda f. Okay. Here we consider the radio frequency band. It's AM, okay, amplitude modulation. The frequency of this band, okay, let's take a look at the figure first. What is AM, okay, amplitude modulation? You know that if you study, okay, in the future, if you go to electrical engineering department, if you want to study electrical engineering, there is a branch of electrical engineering. It's called communication engineering, and amplitude modulation is a type of modulation. Okay, we have frequency modulation, and it's known as FM, right? You may have ever heard FM, and yes, FM may deliver better sound quality. Okay, AM will deliver lower quality of the sound. How does the AM work? Okay, if this is the signal you want to transmit, let's say it's information bit 1 or bit 0 or bit whatever kind of whatever information you want to transmit, like it may be also a part of image or video or something like that. And here you have a carrier signal. Okay, it has a constant frequency. You can see that the length of the wave is constant. Okay, the power is not stretched. Okay, the width is the same for every powers, and okay, if you wanna make the AM signal, okay, it's in wireless communication or in communication engineering, it's known as modulation. Okay, but don't be panicked about the new word modulation. What is that? It's simply the multiplication between the original signal. Okay, any information you want to modulate, any information you want to transmit, that's the decided information, but you are allowed to transmit that information by using this frequency. Okay, it's like if you have ever seen the ancient radio. Okay, you just turn the knob, okay, the bottom in the radio to change your frequency. Yeah, that knob or that rotation means you change, or you look for a new frequency band. Okay, frequency for the amplitude modulation. You change the frequency so that you want to get, or you want to hear something from a different radio station. And here is the desired information. It's only the multiplication between this one and this one. Okay, once you multiply the first row to the second row, you will get the third row. That's the outcome. Okay, and the radio station will transmit this one, okay, to the receiver. Okay, and at the receiver they are gonna detect, okay, or decouple the information from this side once once you know the frequency of the carrier signal. Okay, at the receiver, for example, you hold the radio at home. Okay, your radio will multiply or use some method to detect this waveform. Okay, to get back this waveform, and then you can know, this is the voice of A, B, C, D, okay, from the radio station. Okay, that's the mechanism of amplitude modulation. The important thing for us is that carrier signal is the spatial value for different radio station. Each radio station cannot use the same frequency. Otherwise, you will get the wrong information from different radio station. Okay, there will be interference among several radio stations. Each radio station has to use a unique frequency that is assigned by the government or the local government in that province, in that area. Okay. Okay. For example, in this problem, they say the frequency band, the frequency of this radio station is 1.5 megahertz. So it means the frequency of the green one here is 1.5 megahertz. So what is the wavelength of this one? Okay, just use the ruler and to detect the length here. What is that? Okay. My God, the zoom is close. All right. Okay. That's the C equal to lambda F. The desired expression. Okay, you just move the F to the left hand side, right? Because this is a simple expression actually. Lambda is going to be the ratio between C divided by F, right? And you know that C is 3 times 10 to 8 meter per second, and F is the frequency, which is 1.5 megahertz. All right. Yeah, that will be the way you just substitute this one to this one, okay, to this position, and F like this to the denominator. But the important thing is that you need to where's the here. The important thing is that you have to express this one in a spatial in a plane unit, right, in the typical unit, and that's 10 to 6 hertz. All right. Okay. Once you get this, then we are gonna high school level, and F as the frequency 1.5, 10 to 6, and you get almost 200, right? Because this is number 3 and this is 1.5 is 200. Okay, 200 meter per cycle. Okay, it means the length here is 200 meter. All right, and many of you okay, many of you may have seen the AM, right? And let's move to the again the location of the AM band. Let's move to the location where the AM band is, right? AM or amplitude modulation is right here. Okay, the extreme band like gamma rays and X-ray is over there. The extreme band like gamma rays and X-ray are over there, and frequency for those two bands is very high, like it's 10 to 22 or something like that. AM is around here. It's a kind of low frequency electromagnetic wave. Okay, here is another picture of the whole electromagnetic band. And now we will talk about the next topic in this chapter. It's called polarization of electromagnetic waves, and here we're gonna have more. I would say it's more calculation scenarios. As you have seen the diagram of electromagnetic wave, you can see that there are electric field and magnetic fields, right? And both fields have some fluctuation, or they oscillate in a single plane perpendicular to each other, and the traveling direction is perpendicular to both planes. The electric and magnetic field vibration in the EM wave can also oscillate in a different planes, and this is the situation we're gonna see in this topic. Polarization is the ability of transverse wave to oscillate in more than one direction. Okay, the one you have seen is a simple case of electromagnetic wave. in ถ้าไม่รู้เรื่องตรงไหนนะครับโปรดขัดจังหวะผมทันทีนะครับเพื่อว่าคุณจะได้เข้าใจนะครับถามได้เลยนะครับmost common electromagnetic wave detectors could respond to electric forces on electron in materials, not the magnetic forces. So also the human eyes. Okay, we will depend mainly on the electric field. So we will not depend on magnetic field because many detectors are more sensitive to the electric field. And the direction of the polarization of an electromagnetic wave can be defined to be the direction of the electric field vector, not the magnetic field vector. And here are some types of polarization arrangements. They use mainly the electric field to represent the category of the EM wave. Okay, here you can see that there is fluctuation of the electric field in a vertical way, right? The fluctuation take place, okay, along the y-axis, going up and going down, right? That's what we have seen before, right? That's the typical way of the electromagnetic wave at the beginning. Once we combine the electric field with the magnetic field, you can see the magnetic field on the horizontal plane. Okay, the electric field is in the vertical plane. Okay, but the wave, the EM wave, the electromagnetic wave is moving in this way. Okay, in this direction. This is the plane electromagnetic wave, and it is said to be linearly polarized. Linearly because it's only a vertical line here. When the transverse electric field wave is accompanied by in phase by magnetic field wave. Okay, because we have the magnetic field that has the same peak at the same time. Okay, that has the peak at the same time as the electric field. It's called in phase. Okay, when the electric field is lowered, the magnetic field is also lowered. Okay, when the electric field is highest, you get also highest amount of magnetic field. It's called in phase. Okay. Now let's talk about a more sophisticated type of arrangement of the electric field. Okay. It can happen that once at the starting point, we have the electric field in the horizontal plane like this. Okay, horizontal plane. And once the wave goes by, the electric field goes by like 90 degrees, now the electric field becomes vertical. Okay, and after that, it's going to be again by 90 degrees horizontal. Okay, it change the alignments of the electric field like this, and horizontal and vertical. Okay, like this all the time, and you can see that the electric field can happen in the horizontal plane and the vertical plane, and there is 90 degree of the phase difference. Okay, it means that we have two waves actually. The first wave is the wave that has the E field in horizontal way, horizontal plane. The second wave is the wave that has the electric field in the vertical way. Okay, and once they combine to each other, you're going to see that the electric field gradually rotate once they move in this direction. Okay, it's not just fixed vertically like this. Okay, because it is composed of two electric fields actually. So the electric field actually the electric field that you can observe will rotate like this. Okay, all the time, and that's the rotation. We call this one as we call such type of rotation of the E field as circularly polarized light. Okay, and it consists of two perpendicular electromagnetic plane wave with equal amplitude. Once we have equal amplitude, it means the whole picture will be circle. Okay, because the radius here is the radius in horizontal plane is the same as the radius in the vertical plane. Okay, and there is 90 degree phase difference. In figure 24, the light illustrated is right hand circularly polarized. Right hand because if you stay here, if you are the person who observes here and you watch this E field from the bottom, you can see that the E field rotate like this, right? And yeah, it's if you lay your thumb direction, your remaining forefinger will be in the same direction as the rotation of the E field in this one. Okay, yeah, it's a little bit more complicated than the fixed polarization. Okay, vertical or linear polarization like this. Okay, now let's move to the next case. If we have also two components of the E field, okay, one on the horizontal plane and another one on the vertical plane, but unfortunately the height or the amplitude of the E field in the vertical plane is greater than the E field or the magnitude on the horizontal plane. And in this way, okay, of course, the E field will rotate, but rotate in a different way, because once it's vertical, the amplitude is greater than the amplitude in the horizontal way. All right, and finally, it's going to bring us the oval shape or elliptic shape, right? ภาษาไทยเรียกว่าวงรีครับ okay, and again, the E field will rotate like this, okay, along the propagation direction, and but they don't have the same amount of the magnitude, because the vertical one has greater E field than the horizontal electromagnetic field, electric field. All right, and the phase difference is still 90 degrees. We call this type as elliptically polarized, elliptical polarization. Okay, this is elliptical polarization. Elliptically polarized light consists of two perpendicular waves with unequal amplitude, and they are different in phase by 90 degrees. The illustration of the right-hand elliptical polarized light is in this figure. So in conclusion, we have linear polarization like this. Okay, the oscillation of the E field is only in the vertical line, but for the circular polarization, we have oscillation in both y-axis and x-axis, and fortunately, the magnitude of the horizontal plane is the same as the magnitude in the vertical plane. So finally, we get equal magnitude, and with the equal magnitude, we would, because the E field will rotate, right? We get the circle shape. And on the third figure, we have two components again of the E field, one on the horizontal plane, another one on the vertical plane. But unfortunately, on the vertical plane, we have higher or greater amount of the magnitude, and once the E field goes by, it's gonna rotate, right? Right-hand rotation, and what you can observe the E field by eye is that it will give you the elliptical shape or elliptic like this. Okay, and these are three types of polarization that you may have seen during this class. Let's consider the transverse wave. It is linearly polarized in the y direction. It's gonna propagate like this. Okay. Okay, it has no rotation. Okay, the oscillation just takes place only along the y-axis. It's called linearly polarized in the y direction. And this one is also linear polarization, but the fluctuation or the oscillation take place in in the horizontal plane. Okay, ขออนุญาตครับผมลืมปิดไฟนะครับแสงสะท้อนนะครับขอปิดไฟแป๊บนึงนะครับ Okay. Yes. Let's talk about the device that is related to polarization, and we will bring you to a better situation, closer situation. An ideal polarizing filter, or simply called polarizer, will pass 100% of the incident light polarized in the direction of the filter polarizing axis, but block all light that is polarized perpendicular to that axis. So it will allow every light that has the vertical polarizing axis. But when the light has the horizontal polarization, it will not be able to penetrate this filter or this polarizer. The most common polarizing filter for the light is material that is known in the trademark as Polaroid. I don't know whether you have seen this one or not, but once we complete a little bit the first chapter, I will ask your co-teacher so that we can have a chance to go to the laboratory, the physics laboratory at the school, okay, so that you have chance to make some experiment. Okay, it's widely used for sunglasses. Okay, the Polaroid is used for sunglasses, and apart from that, it's also used in polarizing filter for camera lenses. I don't know whether you have. I don't know whether you are interested in photography or not, but polarizing filter is one of the filter for the camera professional man. All right, the professional cameraman. We have the ND filter, we have UV filter, but polarizing filter is also another type of filter for the professional cameraman. Okay, let's talk about the Polaroid in our subject. Polaroid that has the superscript TM because this is the trademark symbol. Polaroid filter will allow approximately 80% of the intensity of the light. Okay, the polar axis is parallel to a certain axis in the material. It's called polarizing axis, and it will allow 1% or less, or less than 1%. It depends on the quality of your wave. Okay, it depends on the quality of your wave. The polarization is perpendicular to this axis actually. Okay, it's not like the ideal polarizing filter. Okay, ideal polarizing filter will allow 100% of the incident light intensity and 0% of the light in the perpendicular axis. But in reality, in the commercial product, or the filter will allow not 100%, okay, only 80% of the intensity of the wave that is parallel to the parallel axis of the filter, and will cannot completely obstruct the wave that is perpendicular to the filter axis or polarizing filter axis. Okay, it will let 1%. Okay, it will permit 1% of the wave to propagate through the vertical polarizing axis of that filter. Okay, this is the filter in reality, not the ideal one. โอเคก็บทนี้นะครับก็จะเป็นเรื่องเกี่ยวกับการศึกษานะครับว่าแสงเดินทางผ่านฟิลเตอร์นะครับหรือภาษาอันนี้เรียกว่า polarizer นะครับก็คือใช้สำหรับนะครับดูว่าบังคับให้แสงวิ่งไปเฉพาะแนวตั้งเนี่ยนะครับมันก็จะมีแสงบางส่วนถูกลดความเข้มลงครับพอลดความเข้มลงนะครับเวลาฉากลับเราก็จะได้รับแสงที่น้อยกว่าเดิมก็คือมันก็จะมืดลงนะครับส่วนมืดลงมากน้อยขนาดไหนมีความสัมพันธ์อย่างไรเดี๋ยวดูในสูตรนะครับโอเค let's move to the next page. Here is the explanation. in a better way so that you can understand from the figure. Okay, in the light, there could be many orientation of the E field. Okay, we are interested in only the electric field because this is the field that human use several devices to detect. Okay, it's very hard to detect the E field, the magnetic field, but for the E field, human can detect those access easily. Okay, not difficultly. So here is the original light that has several orientations of the E field, and one is propagates through this เดี๋ยวนะครับผมต้องจบคุณกี่โมงนะE to no SCI SCI 33205. What time is that? Where is okay? 14, right? Oh, still long. Okay, 14, 10, right? Okay, and here is the Polaroid filter. It will allow the electric wave or the light, electromagnetic wave, that has the polarization axis in this orientation. Okay, it's called vertical polarizing axis only. So the light that has polarizing axis in a different orientation, like this one or this one in horizontal plane, will not be allowed, okay, to pass through this filter. Okay, only the light that has vertical polarizing axis will be able to transmit through this filter. Okay, but the percent is not 100, it's like 80% according to reality. Maybe in your generation you may be able to build up a filter that can allow 100% of the light. Okay, but at the moment it's only 80%. Okay, polarization filter, namely Polaroid, produces polarized light. Okay, it will block every light component that has the orientation apart from these. Okay, we will talk about the intensity, but before we talk about the intensity calculation, we do need to know some areas in physics. Radiometry is the detection and measurement of optical radiation at any wavelength. It's based simply on the physical measurement. Okay, this is the subject or research area many people are interested in. Okay, and in the radiometry, there is a word which is called irradiance. Okay, irradiance, you may call it. Irradiance is the radiant flux or the power received by a surface per unit area. Okay, it's called irradiance. And the SI unit of the irradiance is watt per square meter, like this. Irradiance is often called intensity, but this term is avoided in radiometry, where such usage leads to confusion and radiant intensity. So we will use in astrophysics, the people call irradiance as the radiant flux, but for us, we will call irradiance somehow as intensity. Let's talk about this experiment. Once your light has several orientations of the E field of the electric field, you place the polarizer with polarizing axis adjustable. Okay, you can adjust the polarizing axis through this knob to just rotate it. Okay, for example, if you let the light, if you move the polarizing axis in this way, okay, only the light that has polarizing axis corresponding to this line will be able to transmit through this filter, and this amount of light will be finally collected to the any measurement device. Okay, transmitted lights linearly polarized parallel to the polarizing axis. Okay, the intensity of the transmitted light is the same for our orientation of the polarizing filter. Whether you leave the blue knob here, or whether up here or right there, you will get the same amount of light intensity. And for an ideal polarizing filter, the transmitted intensity is half the incident intensity. So the intensity after the incident light will be only 50%, okay, of power from the original source of the light. Let's talk about phi, which is the angle that we rotate or shift the polarization axis a little bit from the vertical line. Once you have the light in any polarization orientation, okay, this represents the E field. And once you have the knob like this, okay, only the light that has the polarizing axis like this, okay, will be transmitted through the first polarizing filter. And let's talk about what's going on first. If you have another polarizing filter, you can lay it. Okay, and please make sure that the center of the first one and the second one should be lie in the same way, and should be also at the center of this pipe. And we use photocell to detect how much energy we get. All right. Yes. Once you rotate the knob like this, only the wave that has direction like the E field here could be transmitted. And what's going on? We can have two components, because this is the maximal angle deviation, which is phi, right? We can decompose this vector to the vertical line and decompose this vector to the horizontal line. All right, and once you have another filter, can you guess which component could be transmitted through this polarizing filter? Of course, the polarizing axis is vertical, so only the wave that has the E field in the vertical way will be able to transmit through this filter. And finally, we get only E cosine. Okay, and this light will hit the sensor at the end of this tunnel. Okay, linearly polarized light from the first polarizer can be resolved in two components, E parallel and E perpendicular, right? But E perpendicular has is no meaningful, because it's gonna be perpendicular to the vertical line. Okay, this is the effect of passing unpolarized light through two polarizer. And let's talk about what's going on here in this experiment. What is the final intensity we could get from this experiment? And this question has been raised by someone, and they developed an expression for that. When immediately polarized light strike a polarizing filter and with its axis at angle phi to the direction of polarization, the intensity of the transmitted signal will be equal to I max. Okay, I max the maximum value of the intensity, and cosine square. Okay, cosine square means the box here. Okay, cosine square means the deviation once you have the orientation by phi, okay, from the vertical line. Imax is the maximum intensity of the light, okay, transmitted phi equals 0, and the unit is watt per square meter, right? It's a spatial ratio for us. I is not the current, I is the amount of transmitted at angle phi. Okay, this I is not electric current, is intensity in physics. This relation has been discovered by Malus Law. The relationship is discovered by experimentally by this person. Who, any of you who can pronounce this word? มีไหมครับใครอ่านออกเสียงได้ไหมครับอันนี้เป็นภาษาฝรั่งเศสผมไม่เคยครับ Maybe we call Etiang Louis Malus, okay, and it's simply known as Malus Law. Okay. Before we go to the example, may I go to the toilet for a while? ขออนุญาตเข้าห้องน้ำแป๊บนึงครับ Okay, we arrive at I think it's the third example for calculation, right? Yeah, please keep in mind that the midterm exam or something that will be 100% based on the example here, okay, or the difference will be only the number. Okay, if we have a narrow beam of unpolarized light, okay, with the intensity of I0, the Malus law is somehow I max time cosine square and angle phi, right? I max is maximum intensity. Okay, when we move the polarizing axis to be 0 at vertical moment, and the unit of intensity is watt per square meter. I is the intensity at any angle. Okay, if you rotate this one, okay, you will get the intensity after that depending on the angle phi. Okay, it's discovered by Etienne Louis Malus, right, in 1809. 1809. Here we start with the intensity of I0 at the beginning. It is directed to a pair of polarizing sunglasses. Okay, so we have two pieces of the polarizing filters, right? If the angle between polarizing axes of the two lenses is 30 degrees, okay, let's see, what intensity do you expect to find after the beam passes through the first lens and after it passes through the second lens? Okay, I think there should be no adjective through. It's maybe the wrong one. Okay. So let's, if you don't understand completely what's going on from the text, you may take a look at the figure here. Okay, they have also provided the figure. First of all, you have unpolarized light. Okay, it has different orientation of the electric field, as you know before. And for the first lens, okay, this is your eyeglasses. The first lens is arranged in such a way that the polarizing axis is 30 degree deviated from the vertical line. โอเคเลนส์ชิ้นแรกครับถูกจัดตั้งไว้อย่างนี้แล้วก็ให้มีแกนของการ polarization ครับแกนของการ polarization ก็คือแกนที่ยอมให้คลื่นเหล็กไฟฟ้าที่มีสนาม E นะครับสนามไฟฟ้าเนี่ยเฉพาะแนวนี้เท่านั้นที่ผ่านได้ครับโอเคมา and it is tilted by 30 degree. So of course only the light that has the E field that is tilted like this or deviated like this will take place, okay, will happen after the first lens. And once it's propagated further, it's obstructed by the second lens, but the orientation of the polarizing axis is exactly vertical, okay, in the same way as the vertical axis like this. So the outcome will be the wavelength that has the E field in the vertical orientation like this. Okay, this is the first lens, this is the second lens. We could do it by using the Malus law. But anyway, after the first lens, the intensity will be reduced. Okay, the intensity will be reduced by 50%. So the intensity that you can observe after the first lens will be 50%, or it's 1 by 2 in terms of mathematics. Okay, you will get half of the intensity after the first lens, and once you pass it through the second lens, okay, if you pass it through this, you will get the intensity E2, and I2 could be computed from the Malus Law. Okay, Malus Law here. I max and cosine square theta. And as you know, your I max is I1, right? Your I max is I1, so it's 1 by 2 I0. Okay, and we substitute the amount of angle that is deviated 30 degrees into the expression by Malus, and you could see that I2 is I1, right, times cosine square, and cosine, and the tilted angle is tilting angle is 30 degrees, and as you know, cosine of 30 is square root 3 divided by 2, right? But we need to make the square because it's power of 2. I1 will be the result from the previous or the former expression, right, after the first one. The intensity is reduced 1/2, and is propagated through the second lens, okay, that has polarizing axis in the vertical arrangement like this. Once you substitute I1 by I0 by 2 in cosine square square root 3 by 2, and this is square, this is 3 by 4, and 1 by 2 is going to be 3 by 8. Okay, so the result will be finally 3 by 8 of I0. Okay, please note that here we have a light that is very but it has so much energy because it has several orientation of polarization. For the first lens, the polarizing filter will reduce the intensity of the unpolarized light to be only half of that. So it's intensity of this one, okay, divided by 2. That will be the result after the first lens. But you cannot say the intensity here will be half of this one because this is already the polarized light, okay, and you have to use the Malus Law. It depends on the orientation of the angle difference between the polarizing axis and the incident light. โอเคนะครับภาษาไทยก็คือถ้าคุณมีแสงที่มันไม่ได้ polarize ก็คือมันมีแกนของสนาม E หมุนทุกทิศทุกทางมานะครับก็คือมันความเข้มสูงเนาะถ้าหลักการก็คือว่าถ้าเราเอาเลนส์ Polarized นะครับก็คือตัวฟิลเตอร์เนี่ยเลนส์สีดำที่เป็นกันแสงนะครับกันแสงคำว่ากันแสงก็คือบล็อกแกน Polarized นะครับ Polarizing Axis อันอื่นทั้งหมดนะครับแล้วก็ยอมให้แสงที่มีแกน Polarized ตามเลนส์นั้นเท่านั้นนะครับที่ไปได้แต่เนื่องจากอันนี้เขาไปเอียง30องศานะครับแสงที่ไปได้ก็คือต้องมีสนาม E ที่เอียงมา30องศาด้วยนะครับส่วนแกนอื่นของสนาม E ของแสงครับถูกบล็อกถูกกันไว้ด้วยเลนส์ชิ้นที่1แล้วนะครับโอเคนะครับคุณไม่สามารถบอกได้ว่าอันเนี้ยมันจะต้องมีความเข้มเป็นครึ่งหนึ่งของอันนี้ไม่ใช่นะคือถ้าแสงมามันไม่มี Polarized มันมีทุกแกนโอเคคุณตอบได้ว่าอันเนี้ยจะต้องมีความเข้มเท่ากับครึ่งหนึ่งของอันนี้แต่อันนี้มันเป็นแสงที่ Polarized แล้วนะครับก็คือจัดวางกองมาแล้วเอาเฉพาะสนาม E ที่มันเองอย่างนี้30องศาเท่านั้นครับดังนั้นจะตอบว่าเป็นครึ่งหนึ่งของอันนี้ไม่ได้คุณต้องใช้สูตร Malus Law ตรงนี้นะครับโอเคมา I max cosine square theta โอเคI put the wrong live stream YouTube channel okay yeah that's the example in the calculation of the polarization okay the light is regarded as having a dual nature you can see this word later because it can be also electromagnetic wave it can be also like a particle okay and that's the Broglie wavelength and so on but we will not talk about that in this chapter the light in classical magnetic wave theory we would say that the light can propagate and there is also interference effect the photoelectric effect is the experiment for determining how the atom behave okay that's what you may see in chapter 6 other interaction of the light with matter are best explained by assuming that the light is a particle okay once the light has some interaction with other phenomenon other matter we would consider the light as a particle okay and that's why they say light has dual nature has two natures the first one is the same as the classical electromagnetic wave theory it's only magnetic wave but when it hits or it does some interaction it interacts with some matter or particle we're gonna see that the light is a particle so it can be either electromagnetic wave and particle too okay that's a special thing for the light the light because this is the result of the modern physics or middle age physics okay the light has a number of physical properties some associated with the wave and other with particles so that's the dual nature of the light okay คุณต้องการให้ผมไปต่อถึง14 20นะครับหรือว่าจะขอจบที่14 10เพราะว่าระหว่างสอนผมก็จัดการเรื่องปริญญาตรีด้วยนะครับเขาสอบตอนบ่ายโมงครับซึ่งหลังจากเราเริ่มเรียนได้สักประมาณ20 นาทีครับเพราะเขานัดสอบกันวันนี้นะครับก็เสียเวลาไปกับเขาด้วยถ้าคิดว่าผมเสียเวลากับการจัดการปริญญาตรีด้วยผมก็ใช้10 นาทีนี้เพื่อชดเชยให้นะครับโอเคหรือว่าถ้าคุณอยากเลิกก่อนเลยหรือว่าอย่างไรแล้วแต่คุณครับแจ้งผมมาทางซูมก็ได้นะครับ is there any information นะครับพวกคนที่พิมพ์ชื่อมาครับต้องการให้ผมต่อไปเลยไหมนะครับเพื่อชนเวลาของ605เลยหรือว่าจะเลิกแล้วแต่จริงผมก็เสียเวลานิดนึงอะไรนะครับเดี๋ยวผมได้ยินคุณไม่ชัดครับเนื่องจากเทคโนโลยีเสียงเลิกโอเคครับ so we are gonna quit our lecture today at the moment see you on Friday สวัสดีครับบ๊ายบายครับโปรดอย่าลืมพิมพ์ชื่อนะครับสวัสดีครับถ้ามีคำถามใดก็ถามได้เลยนะครับ ขออภัยด้วยนะครับผมไปใช้ซูมนะครับซึ่งหมดลายเส้นนะครับก็ตัดนะครับเราดูกันที่มีดแล้วกันครับ ซูมOkay,นะครับ for M605 you can start to write down your name and M605 like this. I don't know where we wereคราวที่แล้วถึงตรงไหนเลยครับมีใครจำได้ไหมที่ห้องคราวที่แล้วนะครับผมไม่ได้กดอัดคลิปนะครับ ก็เลยจำไม่ได้เลยว่าถึงตรงไหนนะครับไม่ได้เขียนวันด้วยนะโอเคตรงนี้พูดไปแล้วมั้งถึงตรงไหนครับตรงนี้ไหมประมาณไลท์ต่างๆนะครับนี้เนาะโอเคmoment let me send something to you so that we can see นะครับเดี๋ยวบอกก่อนนะว่าวันนี้มี605มีคนลานะครับนั้นกลัวว่าจะเกิดความโกลาหลนะผมขอเน้นย้ำอีกรอบหนึ่งครับว่าคนที่ลานะครับก็คือพวกนี้นะครับไม่ต้องพิมพ์ชื่อมาก็ได้นะครับสำหรับคนที่ลานะครับเดี๋ยวแจ้งก่อนนะครับเขาก็ลาไปทำธุระเกี่ยวกับจิตอาสาเขานะครับก็คาดว่าจะอยากเป็นส่วนหนึ่งในการสมัครเรียนแพทย์หรืออย่างไรก็แล้วแต่นะครับก็คือจะแจ้งคุณไปก่อนนะครับว่าคนที่ลานะครับผมก็จะเขียนอย่างนี้นะครับเดี๋ยวส่งไปให้ดร.โชคสลันด้วยนะครับแล้วก็เอาใส่ในที่กลุ่มไม่ใช่ดิที่ Google Classroom ของเราด้วยนะครับคนที่ลาก็เขียนว่า on leave to a duty นะครับคนที่ไม่ได้ลานะครับก็จะเช็คตามชื่อถ้าไม่มีชื่อก็จะถือว่าขาดได้คะแนนไปนะครับคนที่ลามีหมายเลข1ครับหมายเลข13นะครับแล้วก็17นะครับแล้วก็22นะครับ23นะครับ26 28นะครับเวลาลานะครับก็อย่างคนนี้เขาก็ถ่ายรูปมาครับบอกว่าลาเนี่ยนะครับไปทำอะไรที่ไหนนะครับแล้วก็ถ้าดีก็คือคุณโปรดมี จดหมายนะครับจดหมายลาอันไม่มีไม่เป็นไรครับแต่ว่าเป้าหมายที่คุณไปครับก็เดี๋ยวมันเป็นข้อมูลส่วนตัวเขานะครับเป้าหมายที่คุณไปนะครับก็มีภาพจะดีที่สุดนะครับอันนี้นะครับคือที่คุณไปนะครับรูปที่คุณไปอันนี้ใบลาครับอันนี้เร็วๆนะมันมีใบบัตรส่วนตัวเขานะครับแล้วก็อันนี้รูปที่คุณไปลาไปทำอะไรนะครับก็ถ่ายรูปมาให้ดูนะครับประมาณนี้นะเพื่อจะได้เข้าใจกันทั้งปีนะครับคนไม่รู้ห้องนี้หรือห้องไหนครับคราวที่แล้วลาแล้วไม่มีข้อมูลอะไรนี่ครับอันนี้ไม่ให้ดูเยอะนะครับเป็นบัตรเขานะครับคุณก็กรอกใบลานะครับโดยเฉพาะใบเป้าหมายนะครับที่คุณจะไปนะครับโอเคไหมก็เขาอันนี้ก็สำคัญในระดับหนึ่งใบลา e+ แต่ไม่มีก็ได้สำหรับผมนะครับแค่เป้าหมายว่าเขาขอตัวคุณไปหรือคุณขอสมัครไปตอนไหนนะครับแล้วก็คุณไปจริงๆก็ถ่ายรูปที่คุณไปมานะครับโอเคไหมก็แจ้งผมมานะครับไม่ว่าทางใดก็ได้ทางเมลทางอะไรก็ได้นะครับก็เหมือนกันนะครับไปอันนี้ไปโรงพยาบาลจิตอาสานะครับเร็วๆนะครับเป็นเขามีใบอะไรบัตรประจำตัวประชาชนเขานะครับก็อย่างเงี้ยนะครับก็ช่วยส่งถ่ายรูปมาให้ดูหน่อยครับโอเคนะครับแจ้งคุณให้เข้าใจกันทั้งปีนะมีคนคราวที่แล้วลาแล้วแบบไม่ได้ส่งอะไรมาผมก็ไม่รู้ว่าจะให้ทำอย่างไรนะครับโอเค Okay, let's talk about our story. I think we arrive at somehow the infrared, right? Infrared has a wavelength that starts from 0.7 micrometer. จังครับเพื่อนบอกว่าเข้าไม่ได้ครับโอ้ผมโอ้เพียบรอก่อนก็ได้ครับมีใครอีกไหมครับมีใครอีกไหมเอ่ยรอก่อนก็ได้โอเคเปิดไว้อย่างนี้นะครับผมไปต่อนะครับเพื่อไม่ให้เสียเวลาครับ604เขาไปแล้วนะครับโอเคalso known incorrectly as heat wave. Okay, but it's not heat wave. Oh, we have already passed this one. Okay. Okay. Infrared rate is used in physical therapy, thermal imaging, infrared photography. We will see the application in terms of infrared photography later. In heating and in the study of our atom vibrations. It is absorbed by atmosphere and it can cause the greenhouse effect. The visible light is what you have already been familiar with. In the order of nanometer, it's used for photosynthesis for the plant. It's used for us to look at something so that we will not hit or catch anything. Is the most familiar form of the electromagnetic wave because it's visible. Okay. The ultraviolet light or the UV light has the wavelength from 0.6 nanometer to 400 nanometer. Okay, it's more dangerous than the visible light. The sun is an important source of the UV light. Yeah. But human also has invented a device to generate the UV light also for spatial application. Most of the UV lights come from the sun, but it is partially or mostly absorbed by atoms in the uppermost sphere. And that layer of the atmosphere is called stratosphere. And in the stratosphere, ozone is produced from the reaction between oxygen and the UV radiation. What about the application of the ultraviolet? ultraviolet or UV light is used in sterilization, okay, in order to keep something like a milk, yogurt, and so on to last longer, to stay longer, so that human can transport them to different locations on Earth. Okay, it generates vitamin D for human body, and unfortunately, it can also cause a cancer to us. Okay, let's talk about the band that is dangerous to us, and that's called X-ray. You may have ever heard this word before, right? X-ray, especially if you want to enter or apply for a school or something, okay, you have to prove that there is no disease in your lung and so on, in your chest. Okay, you have to take the X-ray at the hospital. The X-ray is generated from the acceleration of the electron. Okay, and the wavelength that we call X-ray is from 10 to negative 13 meter, or it's 0.1 picometer. You know, picometer is 10 to negative 12, right? So 0.1 means one more negative, so it's 10 to negative 13. And next one is 10 to negative 8. It's called simply as 10 nanometer. And the most common source for the X-ray, as we said before, we accelerate the electron by any method and let the electron hit a metal target. And once the electron with high energy hits the metal nucleus, okay, they're gonna release some photon, okay, or hit another electron in the electron orbits. They're gonna release the photon, and that photon with high energy is called X-ray. Okay, X-ray has a great penetration ability. It can penetrate several matter. It can damage the or destroy living tissue, for example our skin and other organisms. X-ray fortunately has the good thing, has a benefit. It is used as diagnostic tool in medicine. It is used as a treatment for certain forms of cancer. Okay, and the last band of electromagnetic wave that is extremely dangerous. Okay, it has shortcoming to us. It's called gamma rays. But anyway, human is clever. They will try to apply even something dangerous for spatial benefit, spatial thing. Let's talk about the region of the wavelength that we call gamma ray. The gamma ray is the electromagnetic wave that start from 10 to negative 14 meter. Simply speaking, it's called 10 femtometer. You know, femtometer is equal to 10 to negative 15 meter, right? And yeah, for 10 to negative 14, we need to have 10 more. So 10 times 10 to negative 15 is going to be 10 to negative 14. And to the maximum length, okay, the maximum length is 10 to negative 10, but the closest scale is nanometer. Nanometer is 10 to negative 9. In order to get 10 to negative 10, we're going to say 0.1 nanometer. Okay, that's the prefix unit in physics for us. How could the gamma ray be generated? It is emitted by radioactive nuclei. Okay, if you have the big nucleus And as you know, the big nucleus will not be stable. It's unstable if you let it stay like that. The big nucleus try to decompose itself to be two smaller nuclei, and the smaller nuclei or the small nucleus will release some particles like alpha particle, which is the nucleus of the helium-42, or the beta particle, which is an electron or positron นะครับดีที่ผมเปิดซูมไว้ครับมีใครจะเข้าอีกไหมครับเปิดรอไว้ก่อนนะครับเผื่อมีคนเข้าสาย okay, and that's the two particles we could get from the decomposition of big nucleus. But in some cases, the nucleus or the nuclei is the plural form of the nucleus. In some cases, the nucleus is not stable immediately because it would need it has really high energy for some reason. The nucleus is still vibrating. Okay, the nucleus still vibrates. There is oscillation of the nucleus, and in order to keep it calm, okay, make it calm down, the nucleus has to release the energy, and that energy is released in terms of photon with high energy. The photon with high energy is also known as gamma rays. Okay. What about the ability of the gamma ray? It can penetrate well several meters. It can cause serious damage and absorbed by living tissues. Okay, it's dangerous for us. Even you touch or you absorb the if you absorb the gamma ray for a short time, it's still dangerous. Okay, you need to get some treatment and so on. If we need to work in an environment with high radiation of gamma rays, we must prepare and we have to protect ourselves by wearing the garments, clothes, and these clothes should contain absorbing material, for example, the layers of lead. Okay, we have to get several inches of lead, and we make that thick lead as our clothes in order to protect our bodies from the gamma rays. Okay, you can see it's dangerous. Gamma ray has nevertheless some benefits to us. Human is clever. They use gamma rays for nuclear medicine. They use gamma rays for security reason. They use gamma ray for medical diagnosis and even in the cancer therapy in order to cure the cancer. Okay, and in order to get rid of the cancer, they use gamma ray to make the cell die. Okay, anyway, inappropriate use of gamma ray will lead to cancer. Okay, that's the bad thing because it is full of high energy. Anyway, as you can see, when the wavelength reduces, the energy of the emitted wave increases. All right. ไม่มีใครนะครับขออนุญาตปิดซูมนะครับ here you have big picture of electromagnetic wave in terms of frequency band, wavelength, and shape, and so on, right? You have the scale of frequency almost at the end, and you have at the end the wavelength. Okay, starting from the very long wavelength, to a very short wavelength. Okay, you start from the very low frequency. You know that C is lambda f, right? So you can see that lambda depends on 1 by f or f depend inversely on lambda. All right. Yes. Yes. Let's talk about the band from the left side. Okay. It's known as extremely low frequency. Okay, ELF, and it's safe. Okay, it's not dangerous to us, and it's beneficial if we use in appropriate doses. The wavelength start from 6,000 kilometers. Okay, it's the distance across several countries actually, and the frequency is approximately 50 hertz. Okay, it's really low, and it's beneficial. Next one, we go to very low frequency. Very low frequency would be somehow 1 megahertz. Okay, 1 megahertz to that's frequency, and the wavelength is 300 meter. Okay, still across several provinces, several districts, several states. Okay, it's known as very low frequency. Where could we get the very low frequency electromagnetic wave? You can observe it from the socket at home. You can get very low frequency electromagnetic wave from a transmission line, and this is the transmission tower. Transmission tower is in transmission tower could be found along the road, right? For example, in Thailand, in parallel to the road, you can see the transmission tower. If we move a little bit further, we will meet the low frequency band. Okay, low frequency band means the frequency is on the order of 600 megahertz. Okay, mega means 1 million, right? 500 million cycle per second. That's the region we call low frequency band, and the wavelength is around 60 centimeters. So the wavelength is around twice the length of a ruler. Okay, twice the length of a ruler, 60 centimeters. Okay, and where could we use or found, or we could find the low frequency? Human uses the low frequency electromagnetic wave for television broadcast industry, or for television. And if we move a little bit further, we go to radio frequency band. It's 1 gigahertz, and that's the frequency 1,000 million hertz or cycle per second, and the wavelength is around 30 centimeters. It's 1 ruler, 1 foot, actually 1 foot. You could see this region in you can see this electromagnetic wave in radio receiver and radio communication, whether in wireless communication cellular system. And if we go further, we would reach something like 30 gigahertz. This is the very good band for high data transmission rate, because you are in a very high frequency, and the length is 10 millimeter. Okay, what is that band? It's the band for handy mobile phone, Wi-Fi, or something like that, right? Okay, if you go further, it's gonna be again microwave region, and it can be found in microwave oven. Okay, this one is used for the communication purpose, but this one is used for energy purpose. Okay, because you don't want to transmit information between the cell inside chicken or meat or pork or something like that, right? Because we need only energy to heaten the meat and several stuff for the food, not communication purpose. Okay, and it's also used in satellite communication in microwave region. If you go further, it's infrared region. We use it for also heating application. We use it for remote control also. And the visible light, it's around here several nanometers, right, from the red, green, blue, blah blah blah. And the ultraviolet band, okay, this area, in this band we need to wear the eyeglass, okay, in order to protect the tissue in our eyes, right? Otherwise we're gonna be blind. Okay, we cannot see anything anymore if we don't protect our eyes. And if we go further, it's gonna be the very high region, like 3 pentahertz, 300 pentahertz, and here's the region for the ultraviolet, right? 3 pentahertz, and the wavelength is 100 nanometer. For the X-ray, which is one of the dangerous band, it has the frequency of 300 pentahertz, right? And 10 to 15, right? This one, and the wavelength is 1 nanometer. Okay, 1 nanometer is very, very, very short. Okay, it's very, very short. And because of the short wavelength, it also it returns our frequency in a very, very high amount, like 300 pentahertz. And unfortunately or fortunately, I don't know, it also brings a high energy. Okay, if you go to the chapter 6, you're gonna see this expression E lambda h, no, E HF, okay, which is the expression by Max Planck. Okay, it say that the energy is directly related to the frequency. Once you have more frequency, you are gonna get also more energy. Okay, once the particle has more frequency, it also brings you a great amount of energy. So X-ray is used in some application. For example, if the doctor want to see what's going on with your hand, okay, they're gonna use X-ray to see through see something inside inside your skin. Okay, and you can see that the wavelength is now the wavelength turns out to be very, very, very short. And the last one is gamma rays region. It has many fluctuations at a certain time, and it gives us a very high amount of energy because of its high frequency. Gamma ray is dangerous. That's why you can see this symbol, this sign, right? But as you can see before, human is clever, has made use of gamma ray for spatial application. Now let's talk about the first or second example. I'm not sure. Here we arrive at the problem in calculating something about lambda, which is the wavelength, and frequency. Okay, the formula we need to know is C equal to lambda f. And as you know, c is the speed of the light, right? Which is around 3 times 10 to 8. Okay, for simplicity in your level, in high school level, but actually it's 299 blah blah blah, right? Yeah, we use this expression, but before we simply make the calculation in order to not be the same, exactly the same as what you have seen in Mathayom 5 or Mathayom 4. We're gonna go into the detail of the environment here. They say determine the wavelength of an amplitude modulation wave with the frequency of 1.5 megahertz, and that that the frequency is 1.5 times 1 million, right? Mega is 1 million, 10 to 6 hertz, right? And lambda is what you want to find. C is 3 times 10 to 8, right? Times 10 to 8. What is amplitude modulation? Okay, if you if you have a plan to study bachelor degree in engineering, and of course electrical engineering, as same as me, is one of the branch in engineering, and you may find that electrical engineering has many subdivision, right? Electrical engineering is a department in engineering, and there are some division in there are few divisions in electrical engineering. One of them is communication engineering, and if you study communication engineering, you will learn different types of modulation. Okay, amplitude modulation, or simply speaking, the letter A and M, is one of the modulation technique that the communication engineering communication engineers have invented. Okay, what on how does it work? Okay, of course, the purpose of communication engineering is that you want to transmit the information to the listener from one point to another point, right? From, let's say, from the receiver to the from the transmitter. Let's say this is the transmitter, and here is the receiver. Okay, we use Rx to represent the receiver, and here is the transmitter. You want to transmit some information from this point to this point. Okay, that's the information. For example, in radio communication, the radio station want to transmit the voice of the DJ to the listener at home. Okay, and in this case, the voice that is received by microphone will be converted to the signal, but it's not continuous signal, it is an impulse one. Okay, this is the information you want to transmit. It can have the shape of sinusoidal function like this. Okay, it may have the sinusoidal form like this, and at your radio station, you buy the license, and let's say you are allowed to use only this frequency band. Okay, frequency value 1.5 megahertz. You cannot use 1.6 megahertz at your radio station, because other people or another person has already paid for 1.6 megahertz. You cannot use 1.6 megahertz. You are allowed to use only 1.5 megahertz. Otherwise, you're gonna use the frequency of the other people, and they're gonna force you to jail. All right. If you buy the license for 1.5 megahertz, you can generate the sinusoidal that has 1.5 million cycle of size per second. Okay, you can transmit this one. Okay, in order to use only 1.5 megahertz, and you need to send the information, this one, okay, to the receiver. There is a technique which is called in communication engineering as modulation. Okay, but if you don't know the meaning of modulation, no problem. It's simply the product or the multiplication between this information and the carrier signal. Okay, the carrier signal is the sinusoid that has the frequency of 1.5. Okay, don't worry about the new word, carrier signal. It's a strict sinusoid with 1.5 megahertz. Okay, that's the carrier frequency you can use from the time you buy the license. Okay, once you make the multiplication of the information to this one, you're gonna get the pulse like this. Okay, the outcome like this. And yeah, here, after the product or the multiplication of your signal and the carrier signal, you can transmit this one to the receiver. And the receiver, once they, at the receiver side, once they rotate their knob at the radio receiver to have the carrier frequency like this, exactly the same value as your station, they could there are some technique at the radio to bring the signal, desired signal back. Okay, that's the whole story about amplitude modulation. The way to compute is quite simple because they want to find wavelength, right? So it's lambda. Lambda, what is that? You need to move f, which is another variable, to the left hand side, right? And here you get lambda is equal to c divided by f. And as you know, at your high school level, you have 3 times 10 to 8 meter per second, right? And f will be frequency, which is the value that you are allowed to use, right? Which is 1.5 megahertz. But megahertz is not the standard or basic unit in physics. We're gonna need to convert 1.5 megahertz to simply hertz, right? It's 10 to 6, it's right. And once you know these two values, you just leave c 3 times 10 to 8 here and 1.5 times 10 to 6 here. You're gonna get 3 by 1.5 is number 2, and 10 to 8 divided by 10 to 6 is 10 to 2, right? Which is 100. So it's 200, almost 200 meter. The reason why we don't have exactly the exact 200 here because we didn't use the 3 times 10 to 8 meter per second. This is the exact value of the speed of the light. Okay. Yes. Let's continue our story. Here you would have the whole picture again of the electromagnetic band, right? But where is AM? AM is right here. Okay, it's around megahertz. Okay, the frequency is around megahertz, and the wavelength is around several less than 1 kilometer. Okay, so several hundred meter. So it's a little bit long, right? It's in the long region. And yes, of course, if you go further, you will have the band for television, for frequency modulation. Okay, in frequency modulation, you can adjust or change the frequency a little bit. Okay, you are allowed to use or change the frequency a little bit in microwave, and to infrared, to visible light, to ultraviolet, ultraviolet, okay, UV band to X-ray to gamma ray, and so on, right? As what we have seen before. And the visible light starts from violet or blue to the red one. Okay, and here is the color region you can get from the visible light because it's very narrow here, so they provide a bigger picture. It's expanded, okay. There is an overlap between infrared and microwave, and overlap between microwave and radio wave. Okay, let's talk about the next story in this chapter. Next topic actually, it's called polarization. Okay, polarization is the arrangement of the electric field, actually electric field for the electromagnetic wave. Okay, you know, polarization could take place in also with other kinds of wave, but for us in electromagnetic wave, we will go into the detail in the following. You have seen the diagram of the electromagnetic wave where we have electric field, magnetic field that oscillate in a single plane and perpendicular to each other. It means that the plane for electric field oscillation is perpendicular to the magnetic field oscillation plane. So yeah, both planes are perpendicular to each other. Okay, but actually the electric field and magnetic field could vibrate or oscillate in the different planes other than that. And here we come to the word polarization. Polarization is the ability of the transverse wave to oscillate in more than one direction. This is a special thing of the wave in nature. Okay, it's not simple like you have seen E field perpendicular to B field and so on and blah blah blah. Most common electromagnetic wave detector could respond to the electric field, okay, electric forces or electron in material, not the magnetic field. So it is quite common for us if we use the electric field to represent how the electromagnetic wave is oriented. So it's more convenient to use the magnetic field. So the direction of the polarization of an electromagnetic wave is defined to be the direction of the electric field vector, not the magnetic field vector, because electric field is easily detectable. Okay, we can easily detect the electric field rather than the magnetic field. So that's why scientists or physicists use the electric field to represent how the polarization of an electromagnetic wave is. Okay, let's talk about the first type of polarization. Of course, as we know, electric field is the most important thing because it can be detected easily by human. Here is the electric field. Okay, it's highest, lowest, lower to zero, and lowest as the deep negative quantity, and it turns to be zero and again high and blah blah blah. Okay, it's oscillated is in a circle. The red one is denoted as the electric field. Okay, okay, you can see the fluctuation, the vibration in the y-axis only, and that's why we call here linear polarization. Okay, and according to the induction by Faraday laws or by Maxwell, you can see that the magnetic field is also induced during the electric field happen. Okay, when the electric field oscillates, the magnetic field will be also induced. It's in phase. Okay, the meaning of in phase is that once the electric field is peak at highest value, the magnetic field is also peak at highest value too. When the electric field reaches 0, the magnetic field also reaches 0. Okay, and extremely negative. Okay, electric field will be also extremely negative, and this is the meaning of in phase. Okay, they have the same phase actually. Okay, this is the first type of the polarization in electromagnetic wave. All right, let's talk about the second type. Here you have the original electric field. Okay, electric field like this, and unfortunately, the electric field here, the first one, same as before, it lies on the horizontal plane. Okay, and once you let the time, if you go further by 90 degrees, we have another electric field, but this electric field is in the vertical plane. Okay, same as the magnetic field, but this is the two components of the electric field that could happen. But once we combine, okay, once the nature combine these two electric fields, what we can observe by eye is that the electric field will rotate like this. Okay, rotate, and it goes in this direction. It's called direction of propagation. Okay, it means the electric field will rotate. We don't consider the magnetic field because otherwise it's going to be difficult, and we may not easily understand the concept of this type of magnetic field easily. Okay, what is that? There is fluctuation of electric field in the vertical line according to this component. There is also vibration or the fluctuation of the electric field in this way on the horizontal plane. Okay, this is the fluctuation of the horizontal plane. Okay, and the E field will rotate like that. In figure 24, the light is illustrated in right hand circularly polarization. What is the meaning of circular? It's called circular because the radius of the magnitude in the vertical line is equal to the magnitude in the horizontal line. So yeah, that's why you can say that's why you can see the circle shape here, because the radius is the same. Okay, and what is the reason why we say right hand? Because if you are here and stand here, and you use your right hand, okay, your thumb direction lays in this way, your remaining 4 fingers will represent direction of the rotation of the electric field, and that's why we call right hand. Okay, because if you rotate your right hand, you will get the direction of the electric field. Okay, this is the second type of the polarization. Okay, this is only the second type. The first type is linear polarization, right? Going up, going down. But this one, going up and going down, and going left, going right. Okay, with the same amount of magnitude, and that's why we call circular polarization. Let's talk about the last case. Of course, the electric field would still have 2 components. The first component lies on horizontal plane, and that's why we have fluctuation along this arrow. Okay, whether going up and going down, right? Going down. And the second component of the E field, electric field, is still there, but it's vertical. Okay, it's in parallel to the vertical plane, and unfortunately, the height of this mountain, or the magnitude of the second component of the electromagnetic wave, of the electric field, is greater than the first component of the electric field. So that's why we have the length here greater than the length between left and right. And once you rotate everything from the arrow, you will get elliptical shape, okay, or sometimes we say oval, right? Oval shape and so on. Okay, once it's rotate, okay, because it's a mix of two components of the electric field. Of course, it's gonna be again right hand, but the shape is not circle. The shape is elliptical. Okay, ก็คือภาษาไทยก็เรียกว่าวงรีนะครับโอเคไหม the shape of rotating the E field is elliptical. So in conclusion, we have three kinds of polarization. The first one is linear polarization. The electric field goes up and goes down, goes up and go down, and so on, and the wave travels in this way. And in the second polarization, there are two components of the electric field. Okay, one on the horizontal plane, another one on the vertical plane, and in fact they will be combined to each other, and it's gonna rotate, and that rotation is called circular rotation. And fortunately, the height of the Y component E field is the same as the distance along the X axis for the E field. And that's why we get the circle shape of this fluctuation, and it's called circular polarization. In the last case, we have still two components of the electric field, one on the horizontal plane and one on the vertical plane. All right. Okay. Unfortunately, the vertical fluctuation has greater amount. Okay, is greater than the fluctuation along the x-axis or the horizontal plane. That's why once the E field rotate due to the combination of those two components, the E field rotate, and that rotation has the shape of elliptical shape. So we're gonna say elliptical polarization. Okay, because of this shape. Okay, let's talk about how the wave propagates. Transverse wave linearly polarized in the y direction. They move along the x-axis, right? But the fluctuation takes place in the positive y and in the lower or the negative area y. So that's why we call linearly polarized, because it's going up and down along the y-axis. It's called linearly polarized in the y direction. And if the fluctuation take place along the horizontal plane, and the wave propagates along the positive x-axis according to this arrow, we would call wave linearly polarized in the z direction. Okay, because the fluctuation took place in the z, positive z and negative z. Okay, because of this fluctuation. let's move to the next one. And ideal filter, ideal polarizing filter or polarizer passes 100% of the incident. As you know, you has a request, right, to you has a request to do some experiment, right, about our subject in physics. In this semester, I'm gonna try to ask your co-teacher in order to reserve some timetable and some laboratory rooms for you to get a chance to do some experiment. And one of the experiment that is possible to us in this chapter is this thing. Okay, we would talk about polarizing filter or polarizer. What is the property of the polarizing filter or polarizer? In the ideal case, it will pass 100% of the incident light, and the incident light that will be passed should be polarized in direction of the filter's polarizing axis. Okay, if the polarizing axis is vertical, any wave that has vertical polarizing axis will go 100%. Okay, without any energy loss in the ideal polarizing filter. But it's not the case in reality, because once you mix up some material, those material will absorb some energy. Okay, what about another property of the polarizing filter? It's gonna block all light. Okay, if that light is polarized to be perpendicular to that axis. If the light has the polarizing axis perpendicular to the axis of the lens or the polarizing filter, that light will be completely blocked. Okay, they cannot pass the polarizing filter. And the most common polarizing filter for the light is a material known in the market as Polaroid. Okay, maybe you would not be familiar with this one. Okay, but this is the ancient word actually. Okay, it's popular for people in the past, but nowadays everything is in digital age, right? It's different from this. Okay, sunglasses. Okay, is a product which is made from Polaroid. If you are cameraman or you are serious in taking a photo or photography, there is also polarizing filter. Okay, the polarizing filter is one of the filter that is used for cameramen. What is that? There are neutral density grad filter. Okay, in order to block somehow the light. Okay, the new ND filter for photography. There is another one which is called UV filter. Okay, of course, the UV filter is used to block all UV. And here the third filter, polarizing filter, is the filter that is also used in camera photography by cameramen. Okay, let's talk about the property of the Polaroid, which is the polarizing filter in commercial way in reality. It doesn't pass 100% of the incident light. It will allow only 80%. Okay, not 100%, only 80% or more of the intensity of the wave if the polarizing axis is parallel to the axis in the filter. Okay, it doesn't. Okay, the Polaroid doesn't block completely all right when that light is perpendicular to the axis. It will allow approximately 1% or less of wave. Okay, actually it should tend to be 0, but due to the practical invention, okay, practical generation, it will allow 1% of the wave that is polarized perpendicular to that axis. Okay, let's talk about this figure. You start from the incident unpolarized light. It means the E field is oriented, is pointed, okay, in different way. Okay, the E field points in different direction, almost the complete cycle, and this is known as the unpolarized light. Okay, the unpolarized light will propagate through the polarizing filter, or it's known as Polaroid, and here the blue one is the polarizing axis. Let's say the axis that is the signature, the property of this filter. Okay, if the polarizing axis is vertical like that, this filter will allow the light with only vertical E field, okay, to be able to transmit through this layer. All right, and what you can see is that after the filter, only the light that has electrical the E field that stay vertically like this. Okay, get out of that. What about the light in other orientation? The light in other orientation is blocked. Okay, you can see the orientation of the E field in this way is blocked and blocked and blocked until it has no fluctuation at all. Okay, now we will talk about the calculation, right, of the intensity of the light. Before we talk about the intensity of the light, we have to be clear somehow, because in a special branch of science of physics or chemistry, we have the so-called radiometry, and in this subject they want to detect the particle at any wavelength, okay, and they want to measure any optical radiation at any wavelength simply on by using the physical measurements. Okay, in radiometry, in that society, the people use the word which is called irradiance. Irradiance is the radiant flux received by a surface per unit area. So flux could be the power, and the power and the unit of the power is watt, right? Here we talk about unit area. So the unit of the area is square meter, right? So the unit for the irradiance is watt per square meter. So as you have seen, like something I did, you can imagine that this is actually it looks like intensity, right? Irradiance is often called intensity, but this term is not used in radiometry society, okay, which is a society in physics, because there is another word which is there is another quantity which is also called intensity in radiometry. That's why they say irradiance, in order to avoid the ambiguity with intensity. Okay, In this society, in radiometry, if you say intensity for watt per square meter, they're gonna get confused. Okay, that's why they use irradiance, but irradiance is equivalent to intensity to us in the subject. Okay, in high school level. In astrophysics, the irradiance is called radiant flux. Okay, yeah. But anyway, it's similar to intensity to us here in the high school level. It's watt per square meter. Okay, what is that? You start from unpolarized light like this. Okay, the light that has every direction for the E field orientation. Okay, we call unpolarized light. And here is the filter, polarizing filter, or simply speaking, they call polarizer. Here is the polarizing axis controller. Okay, if you lay out your knob like this, okay, it's tilted a little bit. Only the wave that has the orientation of the E field like this will be allowed to propagate through this filter, and after that the light will go to the photocell tunnel, and there is a background here to detect how much photon they receive, how much intensity the light has delivered. Okay. One thing you need to know is from this figure, if you start from unpolarized light, when the lights hit the filter, and only a single orientation of the light will be allowed to go further, and they found that the amount of the intensity after the filter will be half the incident intensity. Okay, for example, if you transmit 10 watt per square meter here, this is the intensity of the light, you will get somehow 5 watt per square meter after the polarizing filter. Okay, this is the meaning of transmission through the polarizing filter or polarizer. Okay, but what happens if we have two filters like this? Okay, okay. As I mentioned before, we start from the unpolarized light. Okay, that has no unique orientation of the E field. Okay, and once we let it go through the polarizing axis knob like this, only the light with this polarizing E field, okay, or a unique orientation of the E field will pass this filter, and if they go further, you can see that it seems that this component will not be able to transmit or pass this filter, because the vertical line of this filter is the polarizing axis of this filter is vertical like this, right? So we need to decompose this light into the incident E field. Okay, we decompose the incident E field into the vertical one and the horizontal one. And of course, the horizontal one will be perpendicular to the vertical axis. Will be perpendicular to the vertical axis, and it cannot propagate or pass this filter. Okay, and there's of course this one is light is arranged in the same way as the polarizing axis, right? It's straight upward. So this component will be able to transmit through this filter, and that's why we get this component. And this component is called E cosine theta, but we have decomposed E here first to this one to be E, right? And the intensity of the light after this filter, okay, you come with a single unique orientation of the E field. It's called polarized light, right? And once this thing passes, the filter, you will get this one. And there were some physicists who tried to find a relationship between the intensity at the incident side, okay, at the input side, and the intensity at the output side. And that person is known as, I don't know, M605 has someone, right, who can read or who study French, right? I don't know how to pronounce this one. ออกเสียงว่าอะไรครับ605มีคนที่เรียนภาษาฝรั่งเศสนี่นายคนนี้เป็นชาวฝรั่งเศสครับถ้าไม่งั้นเดี๋ยวผมออกเสียงผิดแล้วจะพาคุณผิดไปนะครับ so I don't know คนไหนนะคราวที่แล้วที่เรียนห้องจริงแล้วอ่านภาษาฝรั่งเศสได้ฟังครับโอเคyeah, it's called, I don't know, Etienne Louis Malus. Okay, it's the person who observed the intensity between the intensity of the light at the incident side and at the output side. All right, and the relationship is the I. Okay, I is equal to I max. Okay, I max is the intensity at the input, and phi is the angle between the incident light and the polarizing axis of the second filter here. Okay, and is the multiplication with cosine square, okay, of that phi of that angle. Okay, let's talk about the detail. When the linearly polarized light strike a polarizing filter with its axis at an angle phi to the direction of the polarization, the intensity of the transmitted light will be reduced to I, okay, which is equal to I max times cosine square and phi. Okay, I max is the maximum intensity of the light transmitted when you don't have any tilt at all. Okay, and the unit of intensity is watt per square meter. And I here is the output, okay, the amount of the intensity of the light after passing or propagating through the filter. Okay, the unit of the I is also watt per square meter. Okay, and this law is known as Malus Law. Okay, we arrive at this example. Please note that the example in our lecture note will be chosen as the problem in the midterm exam. So everything that takes place in the lecture will be also the problem in exam, whether in midterm exam or final exam. The difference is only the angle. All right, the difference is only the number in several problems. Okay, but the concept is the same. The question are nearly the same. Okay, let's talk about this example. It's taken from the book number 4. I think it's from I don't know, Young or Survey Bouye, I don't know. I cannot remember actually. If a narrow beam of unpolarized light start with intensity of I0 and is directed to a pair of polarizing sunglasses, if the angle between the polarizing axes of the two lenses is 30 minutes, it's not 30 minutes, 30 degrees, what intensity do we expect to observe after the beam passes through the first lens? There's no through, I think. And after it passes the second lens. Here you can see that if you don't understand the text, just take a look at this figure. They also provide the figure. You know that in physics, it's better to understand if you draw the figure and what is going on with that problem, right? Yeah, it's also the case here. Sunglasses has two lenses, right? This is the first lens. This is the second lens. Okay, and we start with the unpolarized light that has many directions, many orientations of the E field. All right, and the tilted angle is this one. Okay, is 30 degree. Okay, the orientation of the polarizing axis is tilted, okay, or deviated by 30 degree with respect to the vertical line. Okay, and the second lens has the polarizing axis as exactly at the vertical line here. Okay, and of course the output after the result after the first lens will be the light that has only the E field that is tilted by also 30 degrees. Okay, because the filter works perfectly, it completely blocks all other components that have orientation of the E field in different orientations except for this one. Okay, and it will allow 100% intensity of the light that has polarizing axis like this. Okay, the E field orientation like this. Okay, yeah, that's the whole thing that happens to this example. Once you don't understand anything from text, okay, just take a look at the figure. Okay, please be aware that the midterm exam will be exactly the same like here, but the difference will be only the number. Okay, after the first lens, right? After the first lens, before we have the unpolarized light, and after the first lens is this location. What is the intensity at this location? In order to deliver the answer, we have to go back to this figure and look at this sentence. Okay, they say that for an ideal polarizing filter, the transmitted intensity is half the incident intensity. So what does that mean? If you have 10 watts per square meter here from the unpolarized light, and when it goes through the filter, okay, of course the result will be the light that has the E field only directed in this way, but the total intensity will be half the initial coordination. Okay, if you have 10 watt per square meter here, you would get only 5 watt per square meter here at the output. Okay, this is the first property of the ideal polarizing filter. Okay, let's talk about our case. You start from I0, and that's why here you would have anything that is half I0. Okay, so it's 1/2 I0. So you can see that the first question is, what is the intensity or the irradiance after the first range. So we can simply deliver the answer. It's 1 by 2 I0. Okay, according to this property, this sentence, the basic property of the polarizing filter. Okay, 1 by 2 power of the incident intensity power. Okay, let's talk about the second question. Once you have when you let the light pass the second filter, right? Of course, we have only the light that has the tilted E field like this, and how could we how much could we observe, or how intense is the light we could observe here? Okay, you can see that there is orientation again here by 30 degree, right? According to the E field from the incident at this point, right? And that's why we have phi equal phi of phi, sorry ขออภัยด้วยครับบางทีผมจะเรียก phi เฉยๆนะผมออกเสียงแบบเยอรมันครับ is phi, right? In English, phi is equal to 30 degrees, and we have to go back to this formula. Phi is 30 degrees, the tilt angle between the E field and the polarizing axis of that filter, right? And yes, of course, we start here from I0 and we get 1 by 2 I0 here. This is I1, let's say. Okay. Oh my god. I1 is 1 by 2 I0, and here is I2, okay, the result after the second lens. Of course, once you use the Malus Law said I is equal to I max times cosine square angle phi, right? And as you know, our phi is 30 degree, right? And here we need to put I2 at this location. Here we need to put I1 to this location, right? And finally, we're gonna get I2 equal to I1 cosine square 30 degree, right? But you know that I1 is half I0, right? 1 by 2 I0, and cosine 30 is square root 3 by 2, right? You have to square it. And once you make the computation here, 1 by 2 and 3 by 4, it's going to be 3 by 8, right? 3 by 8 I0. And the unit is watt per square meter. Okay, and that's we could get from for this problem. Okay, 3 by 8 I0 watt per square meter. Let's talk about the next thing, the light, which is a member of electromagnetic wave. Okay, can be considered as dual nature, can considered as two things. The first thing is that it can be simply seen as electromagnetic wave, okay, according to the classical theory in physics, okay, because we have light propagation, we have interference effect for the light, okay, it can be reflection, and so on. But from the modern, or I would not say modern physics, it's going to be middle age physics, okay, which is not classical physics, like in I forget his name. Louis de Broglie. Okay, Louis de Broglie discovered that the light actually has the behavior like a particle. Okay, once the physicists observed something from photoelectric effect, they found that the light has some interaction to other matter, and it's better to look at the light or consider the light as a particle. and here is the effect from middle age physics. All right, and we will finally conclude that the light can be considered as wave according to classical electromagnetic wave theory, and considered as particles once it hits or has some interaction to other matter or other particles. The light travels in a straight line path in a homogeneous medium until it encounters, until it is phased with a boundary between two different materials. And here we come to the next topic, which is called deflection, I think. Yeah. Deflection. Okay. When the light travels through a substance, it moves from an atom to another atom of the substance, right? And the time lags caused by the absorption and the re-emission of the light depend on the particular structure of the atoms in that material. The speed of the light will vary among several media because if you look into the micro scale, the light will propagate to hit that atom, and that atom will absorb the energy, and it will release the energy. Okay, and how much the atom will absorb, how much the energy that the atom will absorb, and how long the atom will release the energy depend on different materials. So different materials would have different ability for absorption and re-emission. Okay, and yeah, from this reason, the light will have different speeds among several media. Okay, it's not 3 times 10 to 8 anymore. Once you let the light propagate through different material. Okay, let's talk about this scenario. Let's say you have material A and you have material B. Okay, material A and material B are different from each other. They have different structure of the atoms, and the wave, the electromagnetic wave, which is the light, start from this one. Okay, let's say it has the wavelength like this. Okay, wavelength like this. The wavelength is quite long, right? But once it moves to the second material, the amplitude is reduced. You can see the peak is reduced, and the distance between this bar and this bar also decreases. Okay, you can see that lambda 1, the big one, now turns to be lambda 2. It's smaller. Okay, lambda 2 is smaller than lambda 1. Okay, you have shorter wavelength actually, and the speed will be also different because you have V1 by you have the ability to go ahead by this length. Okay, but here you have less ability to go ahead according to shorter wavelengths, so you will have also lower speed V2. Okay, V2 would be less than V1. All right, and there is value which is called N1. Okay, it's called relative diffractive index. I think reflection index. Okay, it's the direction between the speed of the light. Okay, which is 3 times. I think it's time to let you go out, right? It's time to stop the lecture when I attend to 4 p.m. right? It's 15:50, so we need to quit our lecture right now. If you have any question, just let me know. If not, then see you on Friday morning, right? ถ้าไม่มีคำถามนะครับก็คงต้องจบเลคเชอร์ไว้เพียงเท่านี้ครับพบกันสัปดาห์หน้านะครับและอาจจะสั่งกันบ้านผมก็ลืมสั่ง604นะครับงั้นก็ไม่ต้องสั่งนะ605นะครับพบกันวันศุกร์หน้าครับมีคำถามโปรดถามนะครับถ้าไม่มีปิดห้องซูมนะครับสวัสดีครับบ๊ายบายครับ นะครับไม่มีคำถามเนาะมีคำถามก็ปิดนะครับ